Now that we've gotten our handy dandy quotient rule and you've started memorizing it, right? We can look at some examples here using this quotient rule. So our first example is really going to be a secondary verification problem. We are going to verify that the derivative with respect to x of 2x to the negative third power, we're going to verify that that actually equals negative 6x to the negative fourth. Okay, and why or how we would initially come up with this answer would probably be by using the product rule. So, or not product rule, power rule, the other one that starts with the P. So power rule on this would say that this is derivative of, okay, 2x to the negative 3. You do 2 times, bring that negative 3 down from the exponent, okay, bring it down as a coefficient, and then x to the negative 3 minus 1, which would be negative 4 power. That would give us negative 6x to the negative fourth power. Okay, so we can see from the power rule that this is what the derivative is meant to be, but we're going to verify it by using the quotient rule here. Okay, and to do that, we're going to write our expression 2x to the negative third as a quotient instead. We're starting this off kind of nice and soft here. Okay, we just have 2 over x cubed. Okay, nothing too crazy going on in that numerator or that denominator. But this will give us an opportunity to use the quotient rule. And I'm going to label these as high and low functions and use that low d high minus high d low statement here for us, just since it resonates with a lot of people. A lot of people like that memorization technique. So for our derivative, we are going to take our low function. Low is x cubed. D high, so that is d dx of the high function, which is 2. Okay, minus high function, 2, times derivative of the low function, okay, high d low, so d dx of x cubed, all over low squared. That would be x cubed squared. Okay, so we've gotten the pieces of this derivative written down. Now we need to do some evaluation here. X cubed, and then right here, d dx of 2, the derivative of 2. Derivative of constant, that is going to be 0. Okay, and then minus 2 times the derivative of x cubed. That's a power rule thing. Bring down that 3. Okay, 3x, and lower the power by 1. That would be 2, 3x squared. Okay, and then in the denominator, we have x cubed getting squared. And remember, when we have one exponent raised to another, we're going to multiply those together. So that's x to the 3 times 2, x to the 6th. Okay, now notice that this first term is going to just be 0, x cubed times 0. That's going to disappear on us. And so we have negative 2 times 3, that'd be negative 6, x squared, over x to the 6th. And you can cancel out 2 of those x's in the numerator and denominator. So we're going to cancel those with 2 of those, leaving us with 4 x's in the denominator. So that's negative 6 over x to the 4th. And if we write that as a negative exponent, that is negative 6x to the negative 4 power, which is exactly what we were trying to verify. So this worked out for us. Okay, the quotient rule did what it was supposed to. But that's still, you know, this also makes the point that even though you can do this with the quotient rule, you might not want to. The answer turned out the same, but I would say the power rule was significantly faster and easier here. So you can use multiple rules to verify a derivative or just to take a derivative if you want. You can do this either way, seriously. But this is, I'd say yes, faster with the power rule. So let's make a note of that. Faster with power rule, for sure. Okay, so no single rule is best for every problem, is the point we're trying to make here. All right, so you can't just memorize one derivative rule and then apply it to absolutely everything. Because sometimes that's just not going to work. Certain differentiation rules just will not apply in certain cases. And then also, even if it did apply, it might not be the best choice and it might leave you vulnerable to errors. So you really need to have all the derivative rules handy for you to use. We're building up your toolbox here of different derivative rules to use. Okay, so with that in mind, let's do another quotient rule example here. A little more interesting one this time, perhaps. Derivative with respect to x of x squared plus 3x plus 4 over x squared minus 1. Okay, so let's label this if you like. You don't have to, but I'll call these the high and low functions, or bottom and top, as I was used to them. Okay, and we will do low d high minus high d low. Okay, so here's our low function, x squared minus 1, d high, derivative of x squared plus 3x plus 4, minus the high function, x squared plus 3x plus 4, d low, so derivative of x squared minus 1, all over low squared. That'd be x squared minus 1 squared. Okay, so let's take a derivative here. Well, let's take these two derivatives specifically. All right, we've got x squared minus 1, and then the derivative of this x squared plus 3x plus 4. We're using power rule on this, so bring down your 2x to the first power, plus 3 times the derivative of x, which the derivative of x is just 1. We did that back on the very first page of these notes, back in video 1 of this section. Okay, so 3 times 1, and then plus the derivative of a constant, which is 0. Okay, and then we've got x squared plus 3x plus 4. We're subtracting the second part here, and we're going to take the derivative of x squared minus 1. So power rule on that, bring down the 2, x to the first. So we got 2x, and then minus the derivative of that constant 1, which is 0. Okay. Now in the denominator, you might notice that you could do a little bit of factoring there. X squared minus 1 does factor, but let's just keep it as x squared minus 1 squared for now. and then we'll see if we really need to factor it out later. Okay, because we got some simplification that we can do here. X squared minus 1 times 2x plus 3 minus x squared plus 3x plus 4 times 2x all over x squared minus 1 getting squared. Okay, cleaned up a little bit there. Now let's distribute, see if there are any like terms that we could combine. Okay, in these first terms, we'll have 2x cubed plus 3x squared minus 2x minus 3. And then minus all of this next stuff here, minus 2x cubed minus 6x squared and minus 8x. And why each one of those was minus was because of that negative right there. Okay. And all of that is still over our denominator, x squared minus 1 squared. Okay, so you can see how these start getting a little more expansive sometimes. In this case, we're going to have some cancellation of those 2x cube terms. That does not always happen, by the way. This is just nice. And so we end up having here, it looks like negative 3x squared. And then we have negative 10 x's. And this minus 3 that's hanging around all over x squared minus 1 squared. Okay. Now, in this case here, we notice that there is a quadratic polynomial on the numerator of this expression, and there's a nice, well, semi-nice, I guess, quadratic type of thing in the denominator as well. Quadratic getting squared, that is. We're going to factor this just as a good practice. This is the derivative here, but we're going to just get some practice because you can sometimes simplify these expressions. And if you can, it's a nice thing to do, especially given the stuff that we're going to look at next in this section. If you can simplify a derivative down at all, that can sometimes aid you in further parts of a problem. So here, if we factor that numerator, you could take the negative out first or not, but it would be negative 3x minus 1 times x plus 3. Okay, maybe not the easiest factoring in the world. Some of us might use the AC factoring method on that, or just trial and error to factor, but it is factorable. And then in the denominator, that would factor as well into x plus 1, x minus 1 getting squared. So I guess we could write that. X plus 1, x minus 1. Both of those getting squared. You could distribute that square if you want, since it's a product inside, but notice how none of these factors are going to cancel. Even though you know, we took the time to factor this, it didn't simplify, and that's okay. They don't always simplify, but you generally want to check and see if they can simplify, just in case it helps you further on in the problem. So I'm going to write this again with that denominator of x squared minus 1 squared, just to make it a little more compact again. But you could really put any one of these three forms, any one of these answers would be totally fine. That, or even that. Okay, so there's some examples with the quotient rule.